Okay, last Friday, we used some effort to prove one fact. That is the magnetomotive force generated by the field winding and armature winding will have constant magnitude, always perpendicular to some axis which is lagging the d-axis by an angle psi. So this is the d-axis, which is always in the direction of n. So that is also the direction of the magnetomotive force of the field winding, Fr, because this Fr is always proportional to the field current, and actually equal to the field current multiplied by number of turns of the field winding. For the stator winding, they don't change, they don't revolve, but they have sinusoidal current under the steady state condition. So the sinusoidal current will together generate a total magnetomotive force. So we proved if we calculate two components, one is in the direction of this axis. So this axis has an angle which is psi, which is the power factor angle seen from the generator side for the rest of the system. So depending on the load conditions, so this side can be positive, negative, or bigger or smaller. But if this power factor angle is constant, so in this direction, the magnetomotive force due to the stator winding is 0. But in the perpendicular direction, that's always 3/2 of the peak value. So finally, we prove the stator winding magnetomotive force will be these phases are always perpendicular to that axis, taught based on the power factor of the generator, and also have the constant magnitude. So they can generate the total magnetomotive force if we use this parallelogram. So this will be the magnetomotive force inside of the generator, and that can tell how much voltage is induced. So that will be induced together based on the rotor winding and also armature winding. Okay, so that's it. We only just want to get this conclusion. There's a constant magnitude and direction always pointing to the direction perpendicular to the that axis, M axis. Okay, so we move on, and we also quickly talk about these slides because we want to generate the phasor diagram. We start from the magnetomotive force due to the field winding. We have voltage lagging this F by 90 degrees. So this is not a stationary. So the Fr will revolve counterclockwise together with rotor, and this E also revolve. But for the phasor diagram, we only just define a reference. So similar to the phasor diagram to study the voltage, the current phasors, and you can use anyone to be a reference. So for this case, we can use this E as reference, which means even this E is revolving together with Fr at similar speed of 60 Hertz, but we just assume the relative angle will be same, will be 90 degrees for this case. Okay, and from the previous slides, we prove if there's a power factor of the generator, so which is taught by this frame, and there will be an angle. This is lagging angle by psi, and which means so the Fs will be lagging this E by angle psi. So this angle is actually it's a power factor angle psi. And this stator winding magnetomotive force also induce another voltage lagging it by 90 degrees. So the total magnetomotive force, we call it FSR, will be determined based on this parallelogram. If we draw the parallelogram, that will be total, which means the two voltages also have a total voltage. We call it ESR. Then we'll have this equation. Because E is considered to be the internal voltage source. Why? Because E will exist no matter whether generator is connected to any load. So even under no load condition, so even all the armature current are zero, the generator still have this E as long as the rotor is revolving. So you can have a rotor revolving that will have this FR will induce E. E can be some like a internal voltage. So if you're familiar with some battery, if it's not ideal battery, the battery will have internal voltage, could be 1.5 volt, 2 volts, 3 volt. But when you connect the battery to external load, depending on the resistance built up inside the battery, so the voltage you can measure at the terminal in the circuit can be lower, usually be slightly lower. Okay, so this E will be the internal electromotive force. So this one will be constant. So that one only depends on the field current. Later, at the end of today's lecture, we'll show some example on how we can vary this one. But if we don't change field current, this one will be constant. Okay, this is like internal voltage of some battery. But depending on the loading condition, this voltage will change with loading condition. That's why this one can be slightly smaller than E. Okay, so we know the in terms of magnitude, this capital E in this case will be longest one. And ESR, which is the actual voltage we can utilize to power the external system, if there's some load, it will be shorter. It looks like there's some voltage drop inside of the generator due to the readiness. Okay, so we finish this this parallelogram. So you tell, so even the ESR is the sum of E and EAR, but in this triangle, it seems to be this one is shorter. Okay, it seems to be this one and some voltage drop due to a load inside of the generator, and total will be the internal E. So we can just define the opposite, the negative EAR as some voltage drop. Okay, so this is the longest voltage inside of the generator. This is whatever we can utilize to power external system. And this is the voltage drop inside of generator. So if there's no load, then this one will be equal to that one. But if there's a load, depending on loading the level, so this one can be either shorter or longer, proportional to the current. And this one will become shorter. So if we also draw the current, stator current is always in the same direction of Fs, because this is stator current magnetomotive force, right? So this one is roughly proportional to the current. And we also easily tell, so this voltage is 90-degree lagging this magnetomotive force, which means this voltage is also lagging this current. And this part is orthogonal to this current. Yeah, the negative EAR is in parallel with EAR. So this one is 90-degree leading the current. So which means we can define this one to be the voltage drop on some readiness. So we just define this one to be readiness. So we can replace the negative EAR by the voltage drop of some readiness. So now we have the phasor diagram about the voltage, current, and also voltage drop due to the readiness. Okay, so the current is lagging the voltage by some angle, and this angle is psi. And then there will be some voltage drop due to the current because it is current multiplied by JSAR, it's just some readiness. So this one will be purely imaginary number, which will turn the phasor of the current by 90-degree counterclockwise. So it will have this one orthogonal to the current. So what I mean is if you just extend this line, so this will be 90-degree. So this is the ideal generator without any resistance, without any leakage of flux. What I mean is, so there will be some flux, right? In the magnetic field inside magnetic field inside of generator, but there's no leakage of flux. There's nothing like floods, go outside. Everything can be fully utilized to help connecting the rotor and generator. If that's the case, it's done. So this will be the final phasor diagram. But if there's some leakage floods, that leakage floods can be modeled by some indulgence. We call it the leakage indulgence, or in our circuit, which is readings, a leakage readings. And also the stator winding may also have some resistance. So that will also cause some voltage drop. So which means finally, if we connect the generator to a system, we cannot get this voltage because this is inside, which is like the inside voltage of the DC battery, right? If we just use the battery as analogy, this is like voltage, terminal voltage if it's ideal generator without leakage flux, without resistance. But if it has some resistance, leakage flux, and whatever the voltage we get outside of generator is not even this one, it can be even shorter. So we have to consider voltage drop on the resistance and also leakage readings. So we just call the external voltage as V. I just use our convention notation for voltage. So this is ideal case, but actually we can only get this V, not even this ESR. So there will be voltage drop due to resistance and voltage drop due to the leakage readings, and finally this is the due to the armature readings. So this is the finalized the phasor diagram. So and this way is the final voltage we can get as external of the system. And this one depends on the current. So if the current is 0, which is no load condition, this wave will be equal exactly to this E. Okay. And this is our final equivalent circuit. And we are going to utilize this one for the rest of this section for round rotor generator. Round rotor generator, yeah. Later we'll talk about cylindrical rotor generator, so we will slightly change this equation, but right now this is good enough for most of calculation. And we call this total readings part from that EAR, the other is from the leakage. We call it the synchronous readings. So there are 3 conditions for the generator to operate. When we call it a generator, we suppose it to generate electricity, right, for most of time. But if it's hydro generator, for some time it can be utilized as a pump, which means it will utilize electricity to pump the water up as a storage. So it does operate in 3 different modes, possible mode. Definitely the first one will be generator. For the generator, the magneto-motive force from the rotor winding, the field winding will be leading the total magneto-motive force, because this one is finally generate the voltage to power the external system. So if this IF is leading, FR is leading FSR, so that is the generator mode. So rotor will revolve ahead of the total magneto-motive force. So in other words, the rotor magneto-motive force will ahead of a stator magneto-motive force. So this angle will be positive. If there's no load, so this guy will be same at that one because this stator will become 0. When the FS becomes 0, FSR, the total F will be same as FR. So which is the third case. So the generator doesn't generate any electricity. This mode is called synchronous condenser mode. The generator doesn't generate any electricity because the internal voltage is E, external voltage also E, right? Because the current becomes 0 and this V will finally become E. So remembering from previous session, we developed the formula to calculate IT power over transmission line. So the angle difference tell how much power IT power you deliver. So if angle difference is 0, so if this V and this E in the same direction, there's no IT power. That's also the case we just call it delta R, just indicate their angle difference. So this 0, so there's no IT power, but it still can deliver reactive power, which means the voltage may not be exactly equal to this E. They may have either longer or shorter, depending on you want this generator to generate reactive power or consume reactive power. So, but anyway, that's called a synchronous condenser mode. And the third one will be motor mode. The motor mode means the stator magnetic motor will be leading rotor. So instead of let stator to generate electricity, you give it electricity. Okay, that electricity is stronger than even than the field winding. So if finally you opposite the direction. So if you opposite direction of Fs, this is Fs. So based on the parallelogram, this will be the total magnetic-motive force. So this one will be leading the rotor revolve. So this will become motor mode. We will come back to this one later in the section about some reactive power compensation. Okay, so from now we're safe to use only this equation, this circuit, and this phasor diagram to do all the calculation for the generator. So first, the real power dependent angle, right? This is the fact we already know from previous section. We only just treat this whole branch as some transmission line with reactance and also resistance. So when the resistance is small, which means usually the RA can be ignored compared to the signal reactance. So IT power can be estimated based on this formula. 3 is because we consider 3 phase. The generator still have 3 phases. For each phase, it will be the product of the voltage magnitude on both ends divided by the total reactance, then multiplied by sin delta. So if the delta is very small, this is like roughly sin delta is basically just delta if it's small enough, roughly. But when usually this can be good enough if the delta is less than, let's say, 20 degree or 15 degree. So next we want to study how the phasor diagram can change under 3 typical conditions. For the convenience of drawing the phasor diagrams, so in the following, instead of using E as a reference, we just use voltage as external voltage on the low side as the reference. And we will study the 3 conditions: lagging power factor, unity power factor, and leading power factor. So when we say lagging, leading, the subject is actually the current. Okay, so if we say the generator is operating in the system with a leading power factor, which means the current is leading the voltage, the load voltage. If it's lagging power factor, the current is lagging the load voltage. Okay. So if I have we have the V as the reference, and because the lagging power factor, current will be lagging the voltage by theta angle, theta is positive. Then the voltage drop on the resistance will be the current multiplied by the resistance, because resistance is a real number. Okay, so it will generate a little voltage drop in the same direction of current. The next, we want to draw the voltage drop due to the reactance. So it will be IA multiplied by JXS. Because JXS is an imaginary number, so we need to turn clockwise or counterclockwise by 90 degrees. So which will generate this phasor. And the total phasor based on the triangle, that will be the voltage drop along the internal impedance of the generator. And finally, we get the internal E. So we know for this case, for lagging power factor, E is always longer than V. So in order to have the generator to power some load which require reactive power, you need to make sure the internal voltage E is is higher than the load voltage. That makes sense because reactive power typically from high voltage to the low voltage. And a second case, we still start from the volt V as reference. And basically, we just turn this little triangle by some angle. Because for this case, the theta is 0. Okay, so this triangle will be turned a little bit by the theta angle, 0 for this case. So E is still longer than V. Even the generator doesn't provide any reactive power. It doesn't provide either, it doesn't behave as either the reactive source or load to the external system, but unfortunately the generator itself has some reactive load due to this inductance. So it still need to provide some reactive power just for this reactance. So that will create this triangle. That will make this E be slightly longer than V. Right? You cannot have generator inside to be modeled as capacitance. So it can be, for leading power factor low, that case can be more complex, but let's just draw some extreme case. We can make E be shorter than V. So when the theta become negative, which means the current is leading the voltage by theta, if we define direction of lagging angle as positive, in this case will be negative angle. So we'll turn this triangle further by some angle theta. So this one will be the voltage drop of internal impedance. So in the triangle, we'll have E for this case, which definitely is leading voltage, right? Because the generator, for this case, we still assume it can generate active power. But the voltage can be shorter than V. So for leading power factor, E can be shorter, equal, or longer. Really depend on the phasor diagram. Depend on how large power factor angle you have. If this angle is really large, very likely the E can be even shorter than V. But if this angle is near 0, even it's a negative, but E may still be longer than V. So you need to draw the phasor diagram to determine the length of E. Any question? All right, so next we can study the active and the reactive power output of a generator. Just to make a system simpler, because we definitely need to connect the generator to a system. So in the previous slides, we connect this generator as a source, AC source, to a load. This circuit is similar to the first AC circuit we utilize in the section number 2. But actually, this case can rarely happen in reality, because when we draw the voltage source, it's okay for this circuit. You can have a single voltage source connected to a single load through somewhere. But if this voltage source is a generator need to revolve synchronously with the system, which means the load also need to have, should be another synchronous machine. It can be another synchronous motor and synchronous generator, so they together can have the synchronous speed. It's hard to have a synchronous generator connect to like non-remotional mass or machine. So it's better we connect to a system. But we also don't want to study two complex systems, so we just define the similar system we can utilize in AC power system. We call it the infinite bus. Infinite bus is a single bus. It's an ideal bus, but it's actually the equivalent of a large system. Okay, you may treat this infinite bus as just the simplification of a large system, and the large system, because it's too stable, and the voltage will be always constant. So if it has voltage phasor, the angle never change. The voltage magnitude always constant. And this, because system is too large, no matter the generator is behaving as a source or load, the infinite bus will compensate whatever it provide. So if the generator generate any complex power, the infinite bus will consume everything the generator can generate, or provide whatever the generator need, as if the generator behave like load. that won't change any condition for this infinity bus. So that's called infinity bus. But in reality, it's just the equivalent of a large system. So now we can have a constant voltage at this point. So that will make calculation much easier. So we start from this equation. For this case, we can just assume the resistance to be 0. The complex power will be 3 times voltage times the conjugate current. So radiative power, accurate radiative power will be this formula we proved from the previous session. If the angle, delta angle is small, so it can also be approximated by this formula. This is IT power. Always remember adding this 3 because here we study a 3-phase generator. This one is the torque. Torque will be defined as the power, active power divided by the speed, omega. Okay, and so from the last 2 formulas, we know the power, active power and torque actually change as a sine function of delta. For sine function, which means the 90-degree will have the maximum value. So the power and torque will reach the maximum value when the angle separation between the generator and the infinity bus to be 90-degree. Okay, so when here the difference is 90-degree, so that will be the maximum active power you can deliver to the infinity bus. We also call that maximum value as the limit, the stability limit, because in reality, by increasing delta angle to increase active power, you try to stop before that limit, otherwise the system will become unstable. So the limit simply just you just define, so just replace the sine delta in the top formula by 1. So this will give you the formula to calculate the limit. So the limit depends on the voltage on the both sides. So if you can increase the infinity bus voltage, this power will be increased. Oh, inside of the E, which is the EMF, excitation voltage of the generator, that power also increased. Or you can decrease. So you either increase those voltage or decrease of the readings. That will help increase the power delivery. So there are a couple of good examples on the textbook which help you to learn how to utilize the formulas from previous slides. Let's consider a 50 MVA generator operated at 30 kV voltage. 30 kV is a line-to-line voltage. So this 50 MVA basically just tell you the apparent power, the absolute value of complex power. 30 kV is a line-to-line voltage. So if we want to calculate a single phase, to utilize this formula for just one phase, you need to find this E. So that should be, I think, yeah, this voltage, either E or V, which you need to find the line to neutral voltage. 60 Hertz, and it has a singular reading. Singular readings, which means this one is 9 ohm. Right? And the R will be 0. And the power factor is 0.8. And there's the following 3 questions. The first one, we want to determine excitation voltage of E for each phase, and also the power angle. Angle delta is actually how much the E is leading the voltage, external voltage. The second question is, so if we make the excitation constant at the value from A, and the driving torque is reduced until the generator delivering 25 megawatt, determine the armature current and power factor. So the third one is if generator operating at excitation voltage of part A, what is the steady state maximum power the machine can deliver before losing synchronism. Basically, just utilize the formula from previous slides. Okay. So first, from the parent power 50 and the power factor angle, power factor 0.8, we can get the angle. 0.8 is actually from this triangle. You need to memorize the triangle. So if this one, this is 0.6, and this is 0.8. And this angle is 36.9 degree, right, roughly. You need to keep that in mind. But yeah, this give you more. If you keep 2 digits after the decimal, that would be 36.87 degree. So which means if the diagonal is 50, and so this side is 30 and this side is 40, so be. Yeah, I didn't draw the. Maybe I need to draw the triangle in this way. Okay, so if this is complies a plane, this angle is, this is power factor angle, right? If this is 50 and this is 40 and here is 30. And this is P, this is Q, and this is S. Okay, and the voltage for each phase will be 30 line-to-line voltage divided by root of 3. So that will be this value, and we use the voltage as reference. So current, by using this formula, it will give you this current. So next, we just plug in everything to this formula, and we can get the E, the voltage E. So you tell this voltage is slightly bigger than V, right? Because it's going to, because the power factor is lagging. The external system will need the reactive power. So you need to have the E longer than V to provide the reactive power. Just continue. So basically, you just use those formula in the sequence and to get all the answer required for question B and C. So for B, we use this formula so you can calculate angle, delta angle. And then from here, we calculate current. And this one tell you the maximal. For maximal, and this is just to calculate for the maximum power, what will be the current. Okay. Next slide, we want to talk about one application of using this simplified the generator equivalent circuit model to study how to do reactive power control. Reactive power control means we don't want to change real power or active power. We just maintain P as constant. So the three-phase P will be constant. Also, because here we assume the other side of the system, which is infinity bias, the voltage also constant. So the only thing you can change will be current and excitation voltage E. Okay, so how are we going to change the power factor of the generator to meet the requirement for reactive power? So the three-phase active power can be calculated from the first formula. That's 3 times of the product of the RMS value of voltage and current and also power factor. We can also utilize another formula, which is 3 times the product of the voltage magnitude on both sides divided by the reactance and multiplied by sin delta. Delta is angle by which the excitation voltage is leading the load voltage. Because the power is constant, E is constant, V is constant. So the only thing to change in the first formula will be the product of the RMS value current and this power factor angle. And for the second, this reactance is also constant. So only thing to change will be this voltage, the excitation voltage multiplied by sin delta angle. So we know this one to be constant, and that one also constant. Then we can utilize the phasor diagram to utilize the information on the which to be constant, and we try to change the other variables along certain trajectory that doesn't violate the requirement of being constant. So we start from the V as a reference. So this one will have constant length and constant angle. For this case, it will be 0. And we just draw the phasor diagram for one conditions with current lagging voltage by theta angle. So this is like power factor angle to be positive, a lagging power factor. Because it doesn't have any resistance, so the voltage drop will be inside of generator will be mainly on this cylinder radius. So this phasor is actually it's just perpendicular to the current and leading current phasor by 90 degrees. Then finally, we can draw the excitation voltage E. In this case, it will be longer than V and leading by angle delta. Okay, this is just the phasor diagram for the condition with lagging power factor. Next, we're going to change because we know that this product to be constant, this product to be constant. It doesn't mean the current and IA and the E need to be constant. They can change, but they just need to maintain each item here to be constant. So IA multiplied by cosine theta, which means the IA is projection to the x-axis. So if we draw this triangle, IA multiplied by cosine theta determine the projection onto the x-axis will be constant. So no matter how the IA can change, it can be longer or shorter or maybe even lead the V, but the projection always at that point. So that's from the first equation. And the second equation, the right one tell the E projected to the y-axis will be always same, because that's E multiplied by sine delta, which means the E projection, no matter how the E change, the projection onto the y-axis will be always at that point. So finally, the head of the current phasor will be moved along some vertical line, such that the projection will be same. And the head of E will be moving along a horizontal line, such as projection also same. So we can draw two lines. This first green line does indicate how the current can move. Okay. So the current head will move along this vertical line. And the head of E will move along this horizontal line. But definitely they need to coordinate, such as the phasor diagram still can hold, because you need to tell the voltage drop. So this should be connected by the voltage drop on the cylinder radius. So let's study 3 typical conditions. So we have shown one of the 3 conditions, which is the lagging power factor. And then next we'll move to the unity power factor, which is theta is 0, the current in the same direction of V, and the leading power factor, negative theta. So for 0 theta, so you see the current move to the x-axis, right? The theta becomes 0. And to finish that phasor diagram, the voltage drop, this one will move to this vertical line. And finally, this one will be the excitation voltage. It's still along the horizontal line. And further, if we move the current to have negative theta angle, which is leading power factor, leading the voltage phasor, and the voltage will further move to this location, but still moving along the horizontal line. Okay, so we can ask a question: what did the the furthest condition for E to move, because it seems in this operating in this trend, if we try to change power factor from a positive, 0, and negative, and further negative, finally the E will become shorter and shorter. What is the shortest the E we can have? That is exactly taught from the steady state limit. So the shortest E will happen when the projection is exactly on top of the origin. And that will make the angle, this angle, be 90 degrees. So delta will be equal to 90 degrees. And E will become the shortest one. So why do we want the E to be shorter or this short? Because we want the E to be shorter than V, such that the generator can consume reactive power. But this is a condition the generator can consume the most of reactive power. You cannot change the delta further. So that will be the stability limit. That's the boundary of the reactive power control capability of the generator. So voltage need to be always bigger than this limit. So which means that the power angle delta will need to be less than 90 degrees. Okay, this is basically same story we have shown here. So those are the stability limit. So no matter what condition, no matter you want to vary the active power or vary reactive power, you should never make a delta reach 90 degrees. So delta always need to operate within from between the 90 degree. If you allow the delta to change positive and negative, there's another angle negative 90 degrees. So delta always need to be within negative 90 degree and positive 90 degree. So we just use this example to explain how to determine the limit for a reactive power control. Okay, let's utilize this formula to explain how the reactive power is regulated among those three typical conditions. So reactive power output is controlled by changing the voltage E, the excitation voltage. So based on this formula, we know by changing E, we actually change the reactive power flow. So if I assume delta to be small and we can utilize this similar formula, basically we can compare the E and V, which side is longer, right? If E becomes shorter than V, so the generator will provide negative reactive power, which means the generator will consume reactive power. So if E is longer than V, is higher than V, the generator delivers reactive power to the bus, to the infinity bus, or to the external system. It is said to be over-excited because we need to increase the field current higher than the nominal value, such as to make E to be higher than V. So that's why it's called over-excited condition. Because generators main reactive power sources, they often operated in the over-excited mode. So in practical power system, most of the load actually have internal reactance. As long as it has some inductance, they will behave as some reactance and will consume some reactive power. And the transmission line, the overall complex power consumed by the transmission line also have positive reactive power. We mentioned in the transmission line also reactive load. So finally, the only reactive sources in the power system will be generator and some capacitors. But if you want to put a capacitor, you need to purchase those capacitors, so that will encounter additional cost. So if you don't want to save the cost for adding capacitors, you can let the generator to operate at over-excited condition. Just need to let the generator to have the E to be longer than V, which means the field current is higher than what is needed to operate. So that generator will provide reactive power. So that can save the cost for adding capacitors. In some conditions, if your system has a lot of reactive power, so you want the generator to consume reactive power. So you need to operate the generator to have voltage lower than the external voltage. So the generator will behave as reactive load, not source. So a second example, it just asks you to try, basically just give you some perimeter and values to do some calculation for the three conditions. So for this case, it's same generator as example 1, but we assume the P to be constant 14 megawatt. We already calculated the phase voltage will be a 17.3 kV. We want to calculate the excitation voltage for a power factor of the excitation voltage to be 79.2% of the value from the previous example. And B, we further reduce the excitation voltage to just 59% of the value. And finally, we want to find the minimal E, the smallest E, before the generator will lose synchronism or stability. Okay, we can still use the two formulas to calculate the angle and the current. The first, so the E will reduce to 79% of the value from the example 1. So now you see that now the E is only just around 19 kV, and angle can be recalculated using the new power and the new voltage. So the power angle is 21.8 degree, and current can be calculated at this value. So we found out that actually, because we use the voltage as the reference, we use the voltage as reference. So when you calculate the current, it gets zero angle, which means the power factor is 1, unity power factor. So condition A is just about the unity power factor. So move on for condition B. So voltage is further reduced to 59% of original value. So become even smaller, angle become close to 30 degree. And the current, this value, so you see the angle become 36.87 degree, which become lagging power factor. So this is lagging power factor, leading power factor, because it's a positive sign. Yeah. So become 0.8 leading power factor. So current leading voltage, which means the generator, the external system become reactive source, and generator need to be a reactive load. It need to consume that reactive power. So to do that, the voltage need to become smaller, right? That's why this voltage become just 59% of the original value. The minimal voltage based on this formula, it can be calculated at around 7 kV. And the maximum current will be 2073 at the RMS value, and angle is 68 degree. So this 68 degree, if you go back to this case, that means this theta will become negative, right? But here, it's positive because we use the V as reference. So the current is lagging the voltage by this angle. But if you do the calculation, the phasor will have negative angle because it's in the fourth quadrant of the complex plane. In that example, the theta will become a positive angle, which means you move the current up to about this point. Has very, the answer is about 60 degree, right? Right, 68 degree. So if we try to utilize this phasor diagram to draw it, it will be roughly here. This is very high because it still move along this vertical line. So this is the IA. It's very, then this angle is 68 degree. And if you draw the voltage can be very close to the, will be at the limit. which is this one. Okay, so next we can summarize the result from that example to this table. So here we treat the generator, which include the internal EMF, excitation voltage E, and signal readings at the source. External is just infinite bus. We put all the result into this table for some typical condition. And the first one is from example 1. That's just typical condition for generator to be a reactive source, and the load has lagging power factor. And this is the 3.2A, and this is B. So first one is 3.1. And for 3.2A, and the power factor angle becomes 0. That's unity power factor. And the generator doesn't provide or consume any reactive power, but because generator has internal readings, it still provides a little reactive power only for the internal readings. So that's why the voltage, this E, if you remember the line to neutral voltage, that's a 17.3, but this E is slightly higher, it's 18.7. So that slightly higher voltage is just to provide reactive power for internal readings. And next one, when the power factor becomes leading, and the generator will provide reactive, will consume reactive power. It will behave like reactive load. And the minimal voltage will be this 6.9, and which is leading power factor. Okay. All right. So we'll continue on Wednesday to talk about how the stator current will change with field current. Yeah.
Number 2.9.
Yeah.
Talking about example 2.6, is it referring to the homework or is it textually?
You're talking about the homework? Which one?
The last one, the very last one that wants to write a MATLAB program.
Yeah.
It says based off of example 2.6, right, in MATLAB program, is it referring to example 2.6 as the homework problem 2.6?
No, if you want to find the code, just find the example. The code that the code provided doesn't give you anything about homework, only give you example.
Okay.
Yeah.
Yeah, because I found it in the book.
Right. The toolbars have the code number based on example exactly one-to-one methods. Yeah, but for homework, you need to revise the example code to serve whatever you want to calculate if you want to use that code.
I see what you're saying. All right, that makes sense.